So this is joint work with Eva Chen, who's here, and Jamie Marcus. And this is work that was actually also originated as part of the same IARPA project that Tom was talking about. But actually, I think it has its origins earlier. Someone asked me yesterday for how long I've been working on wisdom of the crowd. And the answer is that we've been working on this problem before there was a wisdom of the crowd. Because this term, as you know, was popularized when this book came out in 2004. But we've been doing work on aggregation of probability, as Tom showed you in some of the slides earlier, way before that. So I think that this, the term that has been very, very successful, has kind of branded this kind of work, has made it very, very popular. But if you look at this definition, you see two things about it. One which I like and one which is questionable. One, it's kind of really vague and imprecise. It's not quite clear, and many people read into wisdom of the crowd a lot of things which I think not everyone intends to. The other one, and that's a point that I'm going to come back throughout my talk, is that it draws a distinction which maybe from a statistical point of view is not quite evident, but I think it's important, between this notion of an elite or some experts and large groups which are where expertise is not necessarily part of it. So I'm going to start with 4 or 5 slides of general comments which are taken from a longer talk that I had on this, which for some of you may be trivial and obvious, and maybe they were discussed yesterday when American Airlines was taking me all over the place before I could get here. So, I think they will help to kind of explain the way I think about wisdom of the crowd and how research in that area should be done. So the first I want to point out to the need to develop a clear and precise definition of wisdom of the crowd, and I think that Lerick, Mans, and Saul went some way in that direction by basically making this definition of that if the crowd's mean is superior to the average of to the average judge. Clint, David Stover, Jason Dana, and Steve Brummel and I have a paper which is now under review in which we offer a different definition, which is more generalizing theirs, namely that the wisdom of the crowd, the presence of a wisdom of the crowd can be observed by comparing, on the one hand, some kind of linear combination of the crowd's opinion to a randomly selected judge. And the point, and what makes this more general, is that when you select a judge from that crowd, and that's in that paper, it doesn't have to be with equal probabilities. In other words, judges can be selected with unequal probability as a function of, say, perceived expertise or their past experience. And so what we do in that paper, which I'm not going to talk about today, is to derive some conditions under which wisdom of the crowd will be observed or not as a function of the degree of bias and differential variability in the population. When was wisdom of the crowd observed, and where was it not studied yet? I think that most of the cases that people have studied belong to the social psychological distinction between intellective and judgmental problems. Judgmental problems being one that do not necessarily have a correct answer, but there are issues of taste and issues of opinions. So most of the work on wisdom of the crowd has been on intellective problems that have a clearly identifiable answer. I think they have been, most of them have focused on estimates of certain quantities of measures of central locations of distribution or single probabilities. The work that we saw yesterday about ranking is kind of an exception. And I kind of just point out that I'm not aware, and I think it's important and probably interesting to do work on issues of wisdom of the crowd in different contexts when people are making estimates of spread of variability, for which individuals are notoriously underestimating variability, in trying to estimate measures of correlations of associations, and I think probably most important, in estimates of single quantities, but not of central location, but of extreme values. For example, if you are an environmental protection agency and you need to set certain thresholds for emissions or some other pollutants, and you want to try to get multiple judges to estimate what is the 99th percentile of a particular distribution, then it's interesting to see whether the same principles will apply as they do in the regular cases. The necessary conditions title is probably exaggerated. I think what probably can weaken it to say important conditions for wisdom of the crowd to work are as following. One, presence of information. There's a very nice example in this paper by Krauss, Rickstone, and Krauss, in which they show results from a large sample of respondents who are asked to make two types of estimates. In one case, and both of them have a correct answer. In one case, it's a regular kind of, here's a jar with many 1,000 marbles, some of them of a particular color. What's the proportion of the red ones? And people estimate it very, very well, just like Galton's estimate the weight. The other problem is a relatively simple, at least for this room, question in probability. The question is as follows. How many times would you have to observe when someone tosses a coin? How many consecutive heads will be necessary so that the probability will match the probability of winning the lottery in Germany? Okay? So you need to do a calculation based on negative binomial distribution. And in that case, it doesn't matter when you're averaging thousands of judgments, they never converge to the right value, because there is not the subset of people who can answer this question correctly is so low that doesn't matter how many people you are using, you never converge to the right answer. The other comment the other requirement that people often invoke is of independence. And I want to stress that when we talk about independence, we talk about procedural independence and not statistical independence. You can never expect to have many, many judges who judge the same quantities and to get them to be independent in the sense of uncorrelated. In fact, typically most judges will be correlated. That's something that permeates all this literature. But you distinguish between this independence and procedural independence, namely people making their judgments individually and without interacting with each other. In fact, in principle, they don't even need to know that there are others who are making the same judgment, so that their judgments are not contaminated by others. And there are at least a couple of papers. Here's one that show that when you allow social influences, that actually diminishes the quality of the aggregation. Then the last point is that you need to have diversity in the group. And the diversity can have multiple facets, but the two that I'm listed here is one is the differences, diversity in opinions, and I think that Stephen is going to talk about this later, about how you can actually push people to think of this problem in more than one way to come up with various estimates. And the other one is that diversity of the population on a variety of other attributes. So this paper that I'm citing here by Jane and Neil Bearden has the following very interesting result. They have groups of people, and they administer personality questions. They administer what is so-called a Big Five, a short version of Big Five, which are 5 personality scales. And then they create groups. And actually, in this case, they only create small groups. I think dyads or maybe triads at most, in 2 different ways. In one case, they bring together people who are as similar as possible in terms of their personality profiles. In the other case, they create a group of pairs or triples which are as different from each other in terms of their personality traits. And then they ask them to make judgments, predicting some football game, predicting a variety of other things. And they find systematically that the groups that created by making people as diverse, as different from each other, perform better. Now, this paper was not published yet. And in fact, Neil tells me that the reason they are not publishing it, they don't have any explanation. There's no reason in the world why creating people who have different personality profiles would do better in predicting football game or in predicting how many blue balls there are in a jar. But I think it's an empirical result, and it points out to this importance of diversity. So now I'm coming to my talk, and so this talk is really kind of trying to answer a couple of quantitative issues about wisdom of the crowd. The first one is, what's the relationship between the group size, the crowd size, and its wisdom? And I'm going to leave these questions to the end. If I have enough time, I'll show you. And I'm going to talk mostly about the second question, which is how to evaluate the contribution of individuals to a crowd. When we have a large crowd, does it always pay to actually use all the individuals? Or are we sometimes better using only a subset of them? And if we use a subset of them, should they all be weighted equally, or are there direct, simple ways to weigh them differentially? And a third question, which is in the background, which is not listed on the slide, is which one is more important, identifying the right people or identifying the right weighting scheme? Okay? And so this is what I'm going to do for the most of the talk. And so we are also using the same forecasting project that Tom described earlier. I will not go again into the details, but just to give you an example, this is what, if you're answering a binary question, that's what it looked like. There was a question, it's very well defined. So by the end of March 2012, the answer, this would have been yes or no, unequivocally. What the judges did, they identified whether they predicted it will happen or not. They were using the slider to come up with their probability. If there was a discordance between their categorical judgment and the probability, so it said, no, it will not happen. But then you assign a probability greater than 50%. You're asked, are you sure? Do you realize there's a inconsistency? And they could say, yes, go ahead, or adjust. And then if they had the opportunity to come and, if they wanted to revise this every time. So what Tom has already talked about, this idea that most people don't answer most of the questions. And if you're to imagine this huge matrix of over 1,000 respondents and several hundred items, essentially most of it is empty. It's over 90% empty, but I hesitate to call this missing value because they are not missing value in a regular, missing completely at random, not missing at random. They are missing in a sense which is related to the nature of what's being forecasted, because it's an indication of what people think they know and how well they know it. And so that's an interesting problem in itself. And I'm going to come back to this rescaled Breyer score in a second. So I want to talk about to mention, before I go into our idea and our data, about 3 methodological comments about how to evaluate work on wisdom of crowd in the context of probabilistic forecast. First, I want to make sure that everyone understands that sometimes you can do very well or very purely due by chance. Just a reminder that imagine that there are 10 items that you're predicting, and each one of them has a probability, a true probability of 0.6. And then by simple binomial calculation, although the probability of each one being successful is 60%, the probability that you have a counter pattern of more than 6 failures is actually very large. It's not negligible. So whatever inferences one tries to make, you have to be very, very sensitive to the fact that chance plays a huge role, and to really make good inferences, you need to rely on very large samples. So I didn't think that one needs to make this comment, but I was reminded of it a few months ago when there was an embarrassingly stupid commentary in the New York Times by David Leonard is his name, the head of their Washington office, where he was saying how the crowds failed because the market, the in-trade, they are called, the in-trade was predicting that the Supreme Court is going to strike down the Obamacare case. And so I think they had a 65 or 70%. And of course, the court didn't. And so the argument was as follows. So this market, based on the wisdom of the crowd, was predicting it will happen, although there were experts who were predicting the opposite, and it didn't happen. Therefore, this is a complete failure. Okay? So the idea, of course, what he forgot to mention, there are also experts who predicted that it will happen. And the idea that you're going to judge the quality of the performance of a particular procedure by one single event, which is probabilistic in nature, strikes me as ridiculous. But so the first reminder is that you need to, of course, use multiple events. The second is that you need to find a way to estimate the quality of the judgments in a way which is relatively free of manipulation and strategic consideration. In this case, we are using the Breyer score. Maybe it should have been before Tom's talk, but you may not think very highly of the Breyer score by now. But in principle, and so what we did in this case, we used a Breyer score, which we rescaled it. We selected A and B such that a perfect score is 100. The worst possible is 0, so it's in the natural 0 to 100, and someone who always answers 50%, 50-50, gets a score of 75. And the last point I want to make is that it's very, very easy in these cases, especially if you don't have very large samples, to overfeed the data and to get deceivingly good results. So I think to stress the importance of out-of-sample cross-validation of all results. So now we come to our key idea in this context of identifying expertise and then building a weighted averaging model that takes advantage of this. And the key idea is really very, very simple. And I'm surprised that people haven't done it before. And for the statisticians among you, it's essentially using the concept of an influence function, which is used in many areas of statistics. And the idea is as follows. Imagine that we have 1,000 people or 100 people making predictions about a particular event. We average their probability judgment. And they said that the group average is 73, and we calculate the Brier score to see how good it is. So now imagine that you are taking out one person from that crowd. Let's take me up. Now you have a different crowd that consists of only 99 people, and you repeat the whole process. Now, with and without me, the results of the means are going to be different, and the performance is going to be different. So you can imagine situations where taking someone out would make no difference. In other words, that's a person that basically just a typical or average person, and with or without him or her is the same. You can imagine situations where if you're taking out a particular person, a particular judge, the group benefits. The group does much, much better. In a sense, the group is much better when this person stays home. And vice versa, you can imagine a situation where when you're taking out a particular person, the group performance deteriorates because that person is the one person that contributes in a positive way to the group's performance. So you can do this now again and again and again for each and every individual and for each or every item that they are predicting. And you can come up with a measure which is the average contribution that a particular forecaster, a particular judge contributes to the crowd. And so, that's exactly what that's our contribution score is. And just to give you an example of what that looks like. Here are, looking at 104 items and 1,200 judges. And we exclude those who answer less than 10 items. So we are left.
Could you go back one slide?
Yeah. No.
No, the other way.
Yes.
So the N is the number of items?
The number of items, yes. Yeah. So in this case, we have 420 people who've answered more than 10 items each. And by using this procedure, see how much they contributed to the score on each one of the items they've answered. And then we calculate for everyone a score. And of course, you would expect about half of them have positive and half of them have negative contribution. In fact, you see that out of 420, 220 have positive contributions. And what this graph is simply showing that the contribution has nothing to do with how many judgments they make. So this is the scatter plot of how many items they've answered. And you see most people are here at the low end. And this is their contribution. And they are not, these two are not correlated. So what we do is the following. We are using this contribution measure to calculate a weighted mean, where the weights are proportional to this contribution measure. And if your weight is negative, you'll get a weight of 0. Okay? And then in order to estimate this in an out of sample, we are doing a jackknifing procedure. So what we are doing, for example, this is a hypothetical example where we have 9 items. So, because that's what we can fit on a screen. So you calculate for every judge what is his or her score, average contribution score based on the items 1 to 8. And you use this to make predictions about item 9, which did not take a part in this computation. And then you repeat this by taking out each item at a time, and you're averaging. So all the predictions that we are seeing are always predictions for items which are not part of the estimation procedure. We'll do even better than that later on. So what I'm going to show you now is I'm going to compare the performance of this, what we call CWM, contribution weighted model, to a variety of other models. And here's a list of the models that I'm going to use. So the first two are just linear pools. The only difference between them is that one uses all the judges, no matter how many judgments they made, and the other one only uses the people who made at least 10. So just an issue of who's included in the sample. The red one, what we call contribution, is essentially a quick and dirty version of our weighted model, in the sense that what it does, it only includes people that have positive contributions, but it doesn't weigh them differentially. So everyone who has a positive contribution gets an equal weight. Okay? So it's somewhere in between the two. And then the other two, the B stands for Breyer weighted models are also weighted averages. But instead, because someone will say, why do you go to all this trouble to calculate the contribution? Why don't you just use past performance, the Breyer score on all the other items? Okay? So these are weighted models, but in which the weights are simply Breyer scores on all past items. And again, either using everyone or only those that had positive contribution. And this is the key summary of our results. So let's look at this column right here, which is the mean score. Remember, chance is 75, perfect is 100. And you see that, of course, not of course, but fortunately, nicely, everything is greater than 75. See that our model is the best, followed by the contribution, which is the same, except that it has different weights. And then followed by the unweighted and the one that are using weights by performance are doing worse than the average weights. And these are just different ways of expressing the same results. So compared to the baseline of the unweighted mean, the linear pool, you have improvement of 4.6 or 2.7. And when you're looking at the relative changes, it can come to about 28%. So why are these models doing so much worse than ours? So here's I think it's kind of a cue to explain. These are the deviations of the Breyer scores based from the average, from the simple mean, based on our model and the models that are weighted on past performance. And I think that there's a key insight here, which it took us a long time to gather, and I think that I'm very comfortable now, which I explain why this works. And the argument goes as follows. As I said earlier, estimates from different people correlate. And therefore, there are many, many cases where people are wrong, and most people are wrong. The people who are getting high contribution scores are those people who correlate well with the crowd in the cases where the crowd does well. But what's special about them is that they are very rarely have this huge error. They are very rarely err with the crowd in the cases where the crowd is wrong. So these are the people who deviate from the crowd, especially in those cases where the crowd basically gets off track. And I think that that's why this performs much better than a regular weighted on performance. Now, remember I said earlier that a better definition of what wisdom of the crowd means is compared it to randomly chosen individuals from the crowd. And we have some simulations here comparing our model with hypothetical crowds. And so we have two hypothetical crowds here. In one case, we simply are selecting responses using a uniform distribution. So we're just generating random responses. And in that case, you get, reassuringly, an average score of 75. The other case, we did something which is more, I think it's nicer. For every single item, we generated a beta distribution of responses which had the property that the mean and the variance of the responses matched exactly the mean and the variance of the actual responses. So the mean predictions were the same, the variance of the predictions were the same. The only difference is that since this beta distribution, these responses were generated independently, individually for every item. Whereas in our model, with our judges, the contribution or the expertise carries within judge, is stable within judge, and carries from one item to another. And you see that even when you are when you are matching the means and the variance of the predictions, still our model operates much better. So the difference between 75 and 81 is how much getting the right mean and variance for every item adds, and the difference between this and 88 is the net contribution of the expertise. So Tom mentioned earlier that these items were taken from a variety of domains. And so we actually went beyond the original 5 domains, and we generated Eva and I mean. We just several hundred items, and we used 11 different domains, but most of the items are, 77% of them are in these 5: business, economy, military, policy, and politics. And I should explain that these are not mutually exclusive. So, because if you have, for example, an item that says something like the Congress is going to pass something about the budget for the, Ministry of Defense or Department of Defense, this is both a military and a policy item. So some items contribute to more than one category. So the idea is, yes, there isn't general expertise, as I tried to show you earlier, but there may also be other domain-specific expertise. So what we are doing here, we calculated scores of expertise separately, or contributions separately for each one of these domains. And you see these are the relationship between them, just to point out that they are all positively correlated. So there is a kind of a single first factor of general expertise, but they are not uniform. And you see this triangle of military, policy, and politics are more highly correlated with each other than all the others. So what we are doing next, on the next slide, we are now doing the same calculations. We're comparing the contribution-weighted model and the unweighted mean separately for each domain. And you see, if you compare these two columns, or this difference, is that in each domain, in every domain, our model does better than, outperforms the unweighted mean. And if you were to actually combine them, the improvement is about 35% relative improvement, with the caveat that they are not mutually exclusive. Okay. Here's another twist on this model, which I think, if people feel uncomfortable with the jackknifing procedure or don't like it or don't understand it, and they say that's not the way things work. This is, I think, what the natural way in which things work. Here's a dynamic model, in which in addition to the first 103 or 4 items, we are adding 90 new items which started, that covered a period from January to April 2012. And the way this worked is as follows. We've calculated for each individual a score based on their first 100 responses. We have a contribution score, so 200 of them are positive, the rest are 0. And now we are using this to predict each one of the future items. But now, sequentially, as a new item is resolved, say item 101, we are redoing our calculations where we are revising the scores and the weights based on the new item. And then 102, 103, and so on, from one item to another. Notice that what could happen in every single stage of this calculation, everyone is included, including people who at stage T have a weight of 0. So it's possible that someone does very, very well for a while, has a positive score, but then for some reason he or she begins to do much, much better. Then after a few rounds, a few iterations, that person will be a 0, and someone who had a 0 weight is brought in. So that's a way of dynamically always improving, keeping only those who have positive contributions up to this particular time. And when we are running this model, again, we see that overall, the contribution-weighted model works better. The only exception, I have no explanation why, is in this area of economy. So clearly, there's a significant improvement, but not in all the domains. OK, so I'm going to go to this in a second. So this is essentially the key of the model. So I think we liked it very much. We're very excited about it. There are certain things about this particular setup which are unique and special, and people may not necessarily find this appropriate. First, there's this huge the matrix is so sparse, and there's so much self-selection in what you answer. Secondly, as Tom mentioned, since these items have a different life length, some of them are for a week, some of them refer to a month, some of them to even longer period, different people can come along and they answer some items just the day before they happen, or they answer it 3 months before they happen. And so therefore, it may very well be there could be some kind of built-in correlation between the contribution and the timing. We have some analysis of the first study which shows that, no, that's not a serious problem, but nevertheless. And so what we're looking for an example where we could try the same thing and see in a more structured and uniform context And we got this data from Cade, Macy, and I forget his two co-authors, their names. But this is a paper that's called Victory of Hope Over Experience. And it has nothing to do with divorced people getting remarried. It's about predicting NFL games. It's predicting NFL games, and they selected people to make judgments about results of NFL games on a weekly basis, and they selected equal numbers of people who are fans of different teams, and what they wanted to see, to what degree people who are fans of, I don't know, the Giants or the Steelers and so on, whether they over the season become better calibrated and can suppress their liking of their team if that affects their judgment. And they actually find that that actually people who are biased, so to speak, in favor of their favorite team continue to be so, even in the presence of feedback that shows this is not their season. So, but the thing that's interesting about this data is that there are these almost 400 people, and every Wednesday they were asked to make judgments about all the games. So the matrix is complete. The matrix of judgment is almost full. It's in one domain, and so it's really very complete. So they're very nicely motivated and incentivized to make. In fact, they also showed me they got emails from some of these people how happy they were to be asked to participate in this study, how much fun it was, and so these are real fans. So what we did, we got their data, and we tried to analyze their data. We actually only use 93 of their judges for no good reason, simply because we didn't need that many. So we selected 3 judges that declared themselves to be fans of each of the 31 teams. There was one team there that they didn't have 3 people, so we excluded it.
You're not going to say which team it was?
Well, first, I don't remember. Secondly, I don't know how exactly they got their sample. I don't think it's an indication of the quality of the team. It's an indication of their procedure who they use for sample. I don't know. So the first revelation we had about this data, which was very interesting, is that people are very bad at making this judgment. So we are going to see, can we identify experts? And the answer is no, because there isn't much expertise in that. I mean, most of the judgments are just barely above chance. So what we did instead, I said, if there is no expertise, let's simulate expertise. And what we did is the following. For each one of these 93 people who were part of our sample, we generated a matched expert. And all we did for that expert is we Winsorized their prediction. So in other words, in all those games where the subject predicted predictions was more than 15 points, these are point spreads, more than 15 points off the actual judgment, we reduce it to 15. Okay, so that's all we do, we just pull them in. And what this does is that if you look at all the judges, the correlation between the prediction and the actual, these are the correlations. The actual correlation, the mean correlation is 0.21. If you look at all these so-called experts, by simply Winsorizing, it goes up to 0.49. And what we created 3 mixed crowds where each one of them had 2/3 original judgments and 1/3 were expert judgments. Okay? And so that's what they are. So is it clear what? Okay. Okay, so here's basically the results. What you'll see, what you're looking for, I should say one thing before that. So as I said, the judges predicted point spreads, and we wanted to operate in the same metric of probabilities and O'Brien score. So the first thing we did, we converted their point spreads into probabilities. There are various ways you could do it. You could do a logistic regression or something. Well, all we did here is a linear regression, which ends up saying that the probability is 0.5 with a slope of 0.003 for every point spread, and this has an R-square of over 95. So it's relatively good. So what we are doing now, we are looking at over the 16 weeks of the season, each one of those a week, and we are looking at the people. The average number of positive contributors by our procedure. And this is overall. And you see that, you know, as we begin, after a few weeks, we basically converge to 31, which was the number of experts. This is the number of people that we generated as experts who were identified, and you see it's very, very clear. It's 31. And the number of people who are not experts who are included in our weight very, very quickly goes down. This is what fraction of the weights of the overall weighting goes to people that are simulated experts and people who are not. And so basically, I'm going to skip a couple of these because the picture is very, very clear. In this particular case, we identify very quickly and very efficiently the experts. So I want to say a few words, which I neglected to say earlier, about a question I asked at the beginning. Namely, what's more important? Namely, identifying the experts or properly weighting them. And we started, I had this intuition, which is not an intuition because it relies on work by Robin Dawes and many, many, many others, that weights don't make such a difference. The most important thing is to, in fact, identify the experts rather than how to weigh them. So in this particular case, it turns out that 81% of the improvement over the weighted mean has to do with identifying the right people and not necessarily with weighting them. So this is my summary, and I want to, I mean, there's nothing here that I didn't say already, but I want to give another twist to what I think we are doing here. I'm thinking of this, I want to go back to the original, this distinction between experts and elite experts and crowd. I think of this as being a continuum that has at one point quality, expertise, and the other end, it has quantity. So put yourself in a situation where you need to make a prediction. You have the options of going and searching for experts or asking many, many people. So if you could, with high certainty, identify the one person, the one expert that you would like to make judgments for you, and if you could justify that their person has an excellent track record, you would never bother, right, going for a crowd and averaging and so on. So if you think that you have the ability to identify quality of expertise and it's available, then I think most people would opt for it. The problem is that in most cases, you don't have this information. You don't know exactly who the expert is. And in fact, you have to fight the fact that people are advertising expertise when in fact it's not present. And in fact, an interesting result is that when people are looking at which judge in judge-advisor interactions, which judges are overweighted, it's consistently people who are overconfident in their opinions, not necessarily who are accurate in their opinions. So it's really very easy to being seduced by confident and confident judges. So what we are doing in this case, you are using as the alternative, of course, let me take a random sample of 1,000 opinion, average them, and so on. What we are doing here is somehow finding a place somewhere in between these two ends. Because we are starting with a large group of people, but we don't pay attention, not equal attention to all of them. Through this iterative procedure where you basically see how well people are doing along the way, you identify a subset of people who are the superior judges, and then you base your predictions on a wisdom of a smaller crowd. So in some ways we are converging to this idea of a wisdom of a smaller crowd, although it doesn't have to be necessarily small in absolute number. It's small only relative to the whole population that you started with. So I think this is a nice and efficient way of identifying this subset of judges, and I think it has very, very good promise to work in many other cases. So I don't know how am I doing on time.
1 minute.
So I can stop here, or I can talk 5 more minutes about this issue of sample size. So I leave it up to you.
You could bring it up in discussion.
Okay, bring it up. So that's the end of my talk. Yes.
So I was wondering, you were referring to the work by Robin Dawes and others about the unit weighting model.
Yes.
In some sense, the black magic there is which cues to include and which not.
That's right.
But that's kind of like what big question is how do you do this? Because you need to have some insight. And I was wondering whether it would make sense to kind of use this approach to do the same thing if you're talking about queues and not about judges, so that you identify the contributions and then make a very simple unit weighting model, or to what extent that has already been done with these influence curves and statistics, because everybody's like, yeah, unit weighting works great, but yeah, the question is which queues to include and which not.
Well, okay. Let me answer this in two or three different ways. So the first answer is that I say, yes, you are right. The beauty of robust improper models, for those of you who don't know, basically say give equal weights to everyone, and it will be just as good as regression or optimal weights. And part of it has to do with the fact that the function that's being optimized in multiple regression is a function with a very, very flat maximum. So even if you're far off from the optimal solutions, you are not doing poorly. And furthermore, this optimum is not unique. There's a series of very nice papers in Psychometrica by Niels Weller about what he calls fungibility of weights in regression, that basically has an algorithm of saying, here's a regression with so many predictions, it has an R square of whatever, and he has an algorithm of generating an infinite number of alternative set of weights that yield the same R square. So that's essentially what the statistical argument in favor of unit weights. Now you're pointing out that this work also says to do well, you need to identify the judges who look at the right cues. So in this context, I don't think this is a problem, because in this problem, everyone uses whatever they use, right? And we don't know what they are using. Simply everyone uses whatever information they have. I want to point to a paper that a former student of mine, Steve Bromell, and I wrote, in which we basically modeled this. So we have a paper in Psychometrica that does exactly that. So essentially said, here are all the cues, here are all the judges, and every judge has their different set of weights. And we make assumptions about how correlated the cues are, how correlated the weights are in the judges. And then we develop a model that basically says, at the end of the day, two judges are going to be correlated to a certain extent as a function of these parameters. And what we find there is much more important to choose the right, the cues are more important than the judges. And therefore, I knew that the weight to be assigned to different judges is going to be less important. So therefore, I'm not surprised by this particular result. And I also think that it's one of these things that unless you do a lab experiment where you control what information you're giving to different people, it's very difficult to control. In other words, you can never control the information that various judges use. And even if you ask them, they're going to give you, yeah, I'm thinking of A, B, C, but there's no way of preventing for them thinking also, maybe unconsciously, about X, Y, and Z. So therefore, I think that's a tricky thing. Yeah. Yes, Robin.
You mentioned somebody's study where if you had a dyad and they had different personality scores.
Right.
The ones that were farther apart did better.
Yeah.
I'm wondering whether or not one of those 5 personality scores tells you something about the person who's willing to differ from the crowd when the crowd's wrong. Because you said from your stuff, you were finding out that was a case where that was good. And that sounds a little bit like it might be related to somebody's personality.
So that's a hypothesis. I mean, I don't know enough about the 5 big 5 other to say that they exist, and probably can name 2 or 3 of them. So, and you're right. When my students read this paper and we talked about it, they all came up with the idea of this. Oh, maybe it has to do to extroversion. This is one of the scale. The people who are more extrovert do blah 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 and so on. So I think it's certainly an interesting idea, and I think that kind of relating this to it's something that we worth doing. Yeah. So you need to find a group of people who are willing to sit through the administration of the big 5. Yes, can you say?
Could you get even better improvement if you formed a smaller crowd of contributors using your measure of contribution?
Yes, I understand.
The contributors and.
So the question is, that's something to be thinking about and tried a little bit. So the question is whether do you mean do everything as we do right now, but instead of using everyone who has positive weights, only use the top 15, top 5%, and so on?
Or you could try different numbers.
Right, yeah.
I'm keying off of Jack's talk.
Yeah. Well, I don't, did you do this? I can't remember if we did this.
Sometimes it was just 5. Sometimes we only had 30 people answered, and based on past, our calculations of past contribution, it was just 5 people.
Yeah. So I think we need, to do that, you really need to find a good data set which is more complete than the ACES one. So we are working now, we are beginning to analyze data that we downloaded from the European Bank, I think, Survey of Professionals. And so they have quarterly projections of multiple items. And I think that may be a good place to try. On the other hand, what I think will happen there is that's a group that, because they're all professionals, the intercorrelations between their judgments are going to be higher. The diversity of, as you found it in many of your papers, the diversity of the judges is going to be relatively small. But we're going to try to look into that, yes. Jack?
Yeah, I had a very similar thought that you could sort of increase the threshold. And my thought was that you're finding that 20% of your benefits are due to differential weighting and 80% to identifying the better judges. And I'm just guessing that ratio might change, that once because some of the people who have positive contribution might just be there by luck, especially if it's a small positive contribution. So people with a smaller crowd, it might push you closer to unit weighting.
Yeah, as I said, that's a good idea, and we're thinking, we'll try it. Mark?
Yeah, related to that, the log factor, can you improve the model by regressing some of the weights, at least for low end, towards 0?
Oh, so in other words, the weights not being strictly proportional, but with some kind of stretching factor.
There could be a Bayesian interpretation of this. There's some recent findings, I think the paper that you forwarded last night, of people that they got very lucky in their one single forecast.
Right.
But they got lucky,
No, I know. I know exactly what you mean. And in the intelligence community, I think this is a problem that plagues them. There's the one, the one single analyst who once in a lifetime makes an off-the-wall prediction and turns out to be true, and then he immediately becomes the expert that everyone reveres, right? He can never replicate the performance.
But that person is also the expert in your model.
Yes. Yeah. Well, but in our model, no one is really based on only one judgment. Everyone has to have at least 10. So and in a dynamic model, it's really based on many more. So I don't think, but it's a valid point. I'm not disputing it. Yes. Tom.
So all your work is on unrecalibrated judgments.
It is. Yes.
So would there be any impact on results if you did this with recalibrated judgments?
Okay. So the answer is I don't know. But let me in our paper, we talked about average and calibrate and average. Now, we bring in a third component, which is positive or negative weight. So now the order, you have not 2 orders, but you have 6 orders already. Calibrate, select, average. So the answer is probably it could help, but I somehow have this sense that I'd like to keep this simple.
You're way beyond that.
Thank you. Yes, sir.
In the case with the 5 categories, did you use the generalized expertise, or did you try to identify experts for this question?
The expertise was identified only on the subset for economics, business. Yeah.
Questions? All right, let's thank the speaker again. And we'll have a 15-minute break.